So the next concept that we want to look at is regioselectivity as far as ketone reactions are concerned. So if we have a ketone such as this, and when you generate the enolate, there are two enolates that are possible. So one is if this, let's say, hydrogen is picked up, okay, then you end up with this enolate. Else you end up with this kind of a enolate. Okay, so of course you have the cis trans isomerism also has an issue here. We'll look at that in the coming semesters. Right now, assume that the problem that we're looking at is only between picking up this hydrogen versus this hydrogen. Okay, so now clearly, if alkylation occurs, let's say with allyl bromide, you end up with mixture of two compounds. Okay, and this is quite normal that if you don't have any other conditions, you usually end up with a mixture of two compounds. Okay, so this is a huge problem that we face when we look at enolate alkylation reactions. And so there are some good ways to address these problems, and that's what we want to look at. Okay, so you'll end up with this type of a compound. Okay, so if this enolate is formed, you end up with this product. If this enolate is formed, you end up with this product. So the reactant here is basically allyl bromide or something like that. So the problem is called regioselectivity problem. And so this is something that we're going to discuss in this lecture. So the first way to think about this is if we can form something that is going to be more stable, since we are quite used to stability as a factor. So let's say I have a choice, and if I'm able to produce this kind of an enolate versus this kind of an enolate. Now, looking at this, similar principles that apply to olefins also apply here. So when you have an olefin, the more substituted olefin is more stable than the, let's say, less substituted one. Okay, so therefore between these two enolates, this enolate is considered to be preferred from a thermodynamic standpoint compared to this enolate. Okay, so if you recall, we have already discussed this concept. So when you have a choice of formation of these two products, and if one of them is formed, then one of them is considered the thermodynamic product and the other one is called the kinetic product. So we'll look at the kinetic product in a short time. But the more stable compound is actually going to be the more substituted enolate. So having said that, now let's look at an example and we will see how well this concept holds good. So let's say we take this ketone with a benzene ring alpha to it. Okay, so when we react this with, let's say, potassium hydride, BHF, now again we have a choice. The choice is between this hydrogen or one of these two hydrogens. Okay, so let's look at the enolate that is formed. So if this hydrogen is picked up, then you end up with an enolate that's going to look something like this. So this is going to be likely, it's going to be a O minus and a K plus. Okay, so now the other possibility is that you get the abstraction of hydrogen at this position and the phenyl ring continues to be on the right. Okay, so these are the basically two enolates that can be formed, and you can imagine that these two would be in equilibrium because we're not doing anything to push the equilibrium towards the low temperature or anything to induce any form of selectivity. So what one could imagine is that when we start with this ketone, you have the possibility of forming two enolates, and it's likely that both these enolates are going to be formed. However, there is one significant difference between this enolate here and this enolate. One is that basically you have an extended conjugated system. Okay, so based on this concept, one could argue that this is the stable or thermodynamically more stable enolate, and therefore this is actually going to be formed. When we do in practice, we do find that this the forward reaction is actually not very favored, and you end up with a situation where the enolate that is formed is actually majorly this one. Okay, so now of course if you now react this with allyl bromide or anything, the product that you're going to get would be the one that is reacting over here. Okay, so let me just write that out so that it's easy for us to follow, and I'll take a slightly different example, or maybe use allyl bromide as the same example here. So number one is KH, and then number two is allyl bromide, and number three is H2O. Okay, so the product that we end up getting is okay. So this tells us that this is under what is known as thermodynamic product, or thermodynamic product is favored. Okay, and by product I mean, what I actually mean is the intermediate, the thermodynamic, the more stable enolate is formed, which then gives you the product. Okay, now the other way in which we are used to reacting to generate enols is to use the trimethyl silyl enol ether. So when we start with this kind of a ketone, when you react this with Me3SiCl in the presence of weak base such as triethylamine, again you have a choice here, and let me just write that out, SiMe3 CH3, or so when we do this kind of a reaction, we observe that the only product that is pretty much formed is this one. Okay, so this is under excellent thermodynamic control, and we exclusively get the formation of this product. Now, so the advantage of using this kind of a trimethyl silyl ether is that one can generate the trimethyl silyl ether and then react it, and you're going to get only a single product that is going to be formed. Okay, now in terms of regioselectivity, how would you do the reaction in a kinetically controlled manner? That is, we started, if you remember, the discussion is how do we access this enolate. So the way we would do this is to use conditions which we are very familiar with, which is LTA minus 78 degrees centigrade in a solvent such as THF. And what ends up happening is that these hydrogens, now you need to understand that we are at extremely low temperatures, and so the temperatures are so low that the populations of molecules that have sufficient energy to cross barriers that we are considering is quite low, and even small structural changes, the change in the or an addition in the barrier, for example sterics, can result in a small increment in the barrier which then becomes inaccessible to most molecules. So here, what is found experimentally is that these three hydrogens are far more accessible. Okay, so they are accessible at room temperature, and therefore they end up being the preferred sites where reaction occurs. So when we add LDA at minus 78 degrees centigrade, the only product that is formed is the kinetic enolate, and this ends up giving us the preferred alkylation product, which is at the less substituted site. So just to complete the discussion here, if we start with this product, this ketone, now if we add LDA minus 78 degrees centigrade, then based on our discussion, this hydrogen is less accessible, these two hydrogens are more accessible, and so let me just draw out the two enolates. So these are the two potential enolates, and so our data shows that this is 100% formed and there is no evidence for the formation of this product. So this is really useful. So when I want to do alkylations at this position, then I generate the thermodynamic enolate using potassium hydride or sodium methoxide or some other base at room temperature, so that I can get an equilibrium over here. Even better, if I want to generate the enolate here, then I actually do the trimethylsilyl enol reaction so that I can exclusively form the more substituted enol. And if I want the enolate to be produced here, then I react it with an extremely strong base at low temperature, such as LDA, and this gives us the kinetic enolate, and that is the less stable product. And we've already discussed about kinetic versus thermodynamic in this lecture previously, and therefore we can actually control the outcome of the reaction. Now, let me stop one last example, which is Me. So if we add LDA at minus 78 degrees centigrade, and then number one, and then number two is reacted with benzyl bromide, the product that is formed is this. Okay, and so the intermediate, as you know, would be the enolate, and studies show that this yield of this enolate is pretty much 100% or quantitative, and or 99% to be accurate. So this is nearly quantitative, and then the alkylation reaction is going to give you the product. Okay, so to summarize this part of the lecture, when we have a situation where you have a competition between two kinds of positions where enolate can be produced. So this is the thermodynamic enolate and this is the kinetic enolate. So the thermodynamic enolate is more substituted, okay, and more stable, all right. And so one of the ways in which you can actually produce this is to use room temperature or even higher temperature, and you react it for a long time. Basically, you give enough time for the reaction to equilibrate, because we're looking at an equilibrium reaction. Whereas with the kinetic enolate, you need to have less. It is basically the less substituted enolate that is formed. It is also less stable. So if this enolate is produced, it's less substituted and therefore it is less stable normally. and we use short reaction times and low temperatures to produce this kind of inhalates. Okay, so we will solve some problems which are related to this, and I hope this will become much clearer as we move forward.